And I think we are in recording.
Yeah. So sign for the coffee cup. It is a paper by Buffaret, Fleury and whatever is the last pronunciation. Okay. Please note I am a math and CS person, so I do not know any physics. Please feel free to correct me whenever you feel whatever I say is completely actually wrong. Yeah. So first experiment we look at is a coin is rolling around about another coin. And completes two full rotations on its own axis by traveling once around the center of the coin. This seems impossible, but a trajectory of a point of the rolling coin touches the center coin only once if the coin rotates twice. Basically, if we start tracking of this point here, we'll see that it only touches here only once before it comes back here. And we could just do this practically as well or find an animatic. Looking into an empty cup illuminated from the side, you see a bright pattern resembling the coin's trajectory. Third thing. A question we really want to answer is this a coincidence? Okay. Let's look at the light pattern. Light over the edge of a circular cup of radius 1, say millimeter radius. Light reflects at point e raised to I phi. Ray crosses the cup edge. Ray crosses the cup's edge again at e raised to I 2 I phi. Makes sense? The angle will just double. So we can parameterize this very simply as e raised to I phi plus e raised to 2 raised to I phi minus e raised to I phi. T is between 0 and 1. This is the reflected ray position. So basically over here is where we are taking the phi and then going to 2 phi. Does that make sense? Now if we look at the disk of radius 1 by 3 rolling around a fixed disk of the same radius, if the disk can flip point phi dash versus roll point phi, we get different trajectories. The phi dash and phi are right here. It's not allowed to flip, otherwise it will just move to phi dash. The rolling curve is given by 2/3 e raised to I theta plus 1/3 e raised to 2 I theta. Sorry, phi.
How do you know that?
How do we know?
Oh, radius 1 by 3.
Yeah,
oh, okay, sorry.
Let's forget. So we can find a tangent vector by differentiation. This can be rewritten as just using the Euler form. This is parallel to the reflected ray. If you look at the reflected ray, these are just parallel lines. Therefore, phi phi is tangent to every reflected ray, forming an envelope. Basically, the tangent to this, the rolling tangent, is parallel to every reflected ray. Basically, they both will contain each other. So, yeah. And again, we can find the exact shape by considering the vectors and everything. And the shape is called a cardioid. Cardio comes from the heart, cardiologist and light rays accumulate at the edges of this curve, and hence the caustic cup here have a bright curve there. This is what we see at the bottom of a coffee cup. The rolling coil and optical caustic are therefore the same mathematical object. This is something which we get to see at bottom of lakes. Raindrops form this pattern on windows, and moving caustic and hot water is how we model convection current. The model given in physics textbook generally goes like this is not how anything really wants to work. The general theory can be found in Benigni et al. Yeah, let's talk about this one. This is also a topic for a Kevin Howe problem. Again, we are given a cup. If we tap 45 degrees from the handle, we get a high pitch, and at 90 degrees from the handle, we get a low pitch. And this pattern repeats every 90 degrees. I can keep doing 45, 45, 90, 90. I'll get the same pattern as we can see on the graph C. So our question should be why. And again, we can see the first frequency is 2800, second frequency is 2940. So, okay. This is just the energy equation from frequency to energy equation. Looks fancy, is not really fancy. S dash is just telling you the direction in which we are considering it. It's not really fancy. contracting at some level. So basically, this kind of motion will have nodes and anti-nodes. Nodes, if you remember from our wave theory, is the parts which are moving the most, anti-nodes are parts which are moving the least.
Is it at the opposite?
Oh, okay. Have it an opposite? Yeah, I think I have an opposite. Nodes are what points that are moving the least, and anti-nodes are the points that are moving the most. And these will be separated by 45 degrees because okay, yeah. And this can be confirmed by the fact that if you hit a cup and then you hold the edge with your fingers, the sound will stop. That tells us that it is the rim which is expanding, contracting, causing this. One way to model this is the edges are just masses with a spring in the middle somewhere. Technically, this is not a very good model because the spring is towards the bottom, but given that the most vibration and sounding is happening towards the rim, we can make this model. Without handle, circular symmetry in all angles should give us the same amount of sound. With handle, the symmetry breaks. And impact at 0 degrees, impact straight at the handle, will excite the anti-nodes at 0, 90, 180, 180 and 45, excites the nodes at 0, 90, 180. So handle on anti-node, which means that a lot of mass has to oscillate and hence lower frequency should be given to us. Handle on the node means less mass to oscillate and higher frequency. So f2 minus f1 is 1 by 2 pi. This is just the frequency equation from the spring equation. 1 by 2 pi minus, and this we can use the Taylor approximation to come to something of the form minus f2 is roughly equivalent to difference of mass divided by 2 times the mass. This means that somehow we can figure out the mass of the handle of a cup given the mass of the cup and a frequency detector. If this were very contrived way to do for yes. But yeah, so we can just find out that the
yes, already given the solution. That's not a good question.
yeah. Now this tells us that for the question which these people considered with their cup, they found it that it was 9.5% of the mass within the handle. And they cross-checked it with Arjun principle, that is pretty much that they just submerge the cup, not the handle, and measure how much water escaped, and then they submerge the entire cup. This can compare it.
To find the mass of the.
Find the percentage of the mass which the handle is holding.
Yeah, so where do they would have
A weighing machine.
yeah.
A weighing machine won't do work, right? You have to cut the handle off. You have to destroy the cup.
Interesting.
Okay, full analysis will require us to talk about modal mass and modal shift.
Wait. Go back to the equation.
Yeah, F2 and F1 is
Higher and lower.
yeah.
Oh, I thought that. Okay, fine.
Yeah.
That makes sense.
That would be it's fine.
Yeah, interpreted it that.
Yeah, and obviously we will need to talk about a lot of other things here that, like in reality, it's not as clean, and that is the reason we have a 1.5% error somewhere. Applications is that this kind of things are normally used for health monitoring. And this is basically the workaround principle of a sonography. We use a gel in that case, which also is can be used to detect defects in buildings and bridges, and in cups as well. Quality control. This is a question which we have given in STEMS before now. Basically, when you stir the coffee, you will find that the sound pitch rises over time as the bubbles start to dissolve. The question when we gave it in STEMS was you were pouring a soft drink. In this case, the sound is coming from the spoon rubbing against the base and it's propagating to the liquid. In our case, you are pouring the soft drink and the sound was coming from the soft drink hitting the base of the glass. We will see no such effect with plain water, and hence the question was given on soft drinks. So height of liquid is H, boundary condition at bottom that there is no displacement, and top atmospheric pressure. So again, pressure node on top, pressure antinode at bottom. Again, this is the same flow of pipe thing from waves. First node wavelength is lambda equal to 4h. Resonance frequency again. K is compressibility, rho is density. small, we can take the mixture compressibility of wave and air, go through the procedure. See, the basic point is we do not know K, rho is known to us. Compressibility is the main problem of what we do not know. And we are just trying to figure that out in this case. That how much is the thing willing to compress. So, compressibility of water and compressibility of air, the bubbles which are trapped inside. And we all also know the ratio of these things. Like we know the ratios are known to us beforehand. We just don't know in what, like given the mixture ratio, like what ratio we have mixed air with water, we want to find the compressibility. A common error in this question was put on stems was that a lot of people just made the assumption that we can just take the weighted average. We really can't. We need to go through this entire procedure. For an air water mixture, we can keep calculating. And this can be used to actually figure out, because we could have measured the frequencies here. This can be used to figure out how much carbonation, or in this case, how much foam was there in our water. And this is called good formula, by the way, because I think this paper came from, this entire experiment came from a paper called hot chocolate effect by this guy. Yeah. Again, basic complication is that there is bubble resonance. We have assumed foam to be a uniform thing. Second, sound is absorbed by these things. Bubbles get bursted when the sound travels, which we are again not accounting for. And there are dampening effects.
Okay, but is the error given?
What?
Is the error given?
The error. Yeah. For the error.
What?
No. Graphs are given.
Like the real value versus.
Yeah. Oh, the real value. We do not know the real value. What's the method of finding real value?
It's not a method.
The problem is that the only way we know how much carbonation is in coffee would be a method of this type only. It is used in something called broadband acoustic resonance resolution spectrum, which is exactly what we are doing here, trying to figure out how much gas is dissolved in the chemicals at the time. And this is literally how this works. Like I tried to Google this machine up. It's basically something which is, it's a small hammer which keeps hitting the beaker at the bottom and tries to keep recording the frequencies. Okay. Yeah, this is called the Einstein's paradox. That is, when we stir tea, leaves gather at the bottom center. But leaves are denser than water, so they should be pushed outwards, but they move inwards. So, scary math. Yeah. Let us say the entire water is rotating with some angular velocity omega. Then the pressure field, the rotating frame, is gradient of pressure is rho into gravity minus rho acceleration, where acceleration is just the centrifugal acceleration.
Go back.
Yeah. Now we are just looking at the radial component, the change in rate of change in the radial component of pressure is based on, like it's just it's just density into radius times the angular velocity square, and the pressure component moving upwards is just rho gh, and we are differentiating with z, which is h, so minus rho g. But just combining all of that, we get this, and we are assuming it to be an isobar. The pressure, the surrounding pressure is not changing. It's a logical assumption to make in this regard, I think, which allows us to assume this entire term to be 0 and move things aside and get something of this sort.
Okay, what's your?
Isobar.
The Canadian roads.
So if I assume isobar, then I can just move this here and take rho and g below here, rho gets cut and we get this z0 for the initial condition. Make sense? That's the isobar assumption for this case. So if we just naively use Bernoulli, we'll get a wrong sign for the centrifugal term. Bernoulli's principle applies along individual streamlines, each with its own constant. Bernoulli normally does the pipe. We do not assume this to be a circular plane. In a rotational flow, this constant will vary between all the streamlines.
Integrating those streamlines.
What? Integrating over the streamlines. No, streamlines are affecting each other.
Oh.
And I think you will.
With
Yeah.
viscosity.
velocity is 0 at bottom, only hydrostatic pressure remains.
Wait, is that an example of some function?
What?
Velocity gradient is opposite.
Not really. It's one of the worst assumptions we are making. It's a very egregious assumption to make. It's just made in this case because making any other, like without any of such assumptions, getting any of these extra terms will become a headache for us.
So wait, go back. The thickness, are we ignoring the thickness in the boundary?
Yeah.
You cannot simultaneously assume that and the velocity is zero. That is such a bad.
Yeah.
Like one of them, if you assume there is a viscosity at the bottom, fine.
Yeah.
If you assume velocity is there, fine.
Yeah.
But both of them.
So hence we are making a boundary layer, right? There is 0 till here, and after that there is velocity. Yeah, that is egregious. Like, what is egregious? I do not like it. So yeah, bulk flow solid rotation. Isobars bent outwards. Boundary layer only hydrostatic term. So isobars bent inwards. Basically, the entire reason for making this assumption is because we want to claim that here, where only hydrostatic forces are remaining, the T will move inwards and everything else will just make a parabolic flow towards the top. Yeah. I basically believe that this assumption is made with the experimental result in mind. They're like, okay, this is what experiment is showing, now we want to theoretically justify that. Yeah. So pressure gradient at bottom drives the fluid inwards. Incompressibly, fluid must rise somewhere. Vertical circuits develop. Blah blah blah. Vertical circuits. And dense particles cannot follow offending current at the center. As you can see, the offending current at the center is much weaker, like is rather weak. So they will accumulate where current starts. And light particles are carried outward at the surface. Like the particles towards the top will just behave as we had expected them to go outwards. Towards the bottom will behave weirdly. A better way to do this is basically if you put TDs and then put some black pepper on top, and then you do this. What? Surface tension.
That's a reason.
No, black pepper surface tension. Yeah. Oh, you
Break
like
the
this?
surface.
No, no.
Then
Oh, so in that case you have to add a little bit of soap to make the surface.
no, what is
No, I'm saying black. Oh, just putting black pepper for the top part behaving normally is apparent. The
why
bottom,
is black pepper useful?
because black pepper is lighter. You just need a lighter particle. Basically, the lighter particle will be on top, and it will just go through the secondary flow and it will just move towards the side and rotate it.
Yeah.
And the bottom particles will move towards the center and rotate.
Yeah.
That's what we want to show. The paper does it by saying that some leaves will be lighter and they'll be on the top, and you'll notice them. I'm saying that in a
Okay,
demonstration,
that's it.
we are better off adding a little black
So,
pepper.
observing more.
Yeah.
Okay.
What creates this current in the first place?
This will literally be the fluid dynamics. Answer fluid dynamics.
Can you go back two slides before?
Here?
No, it's not about here.
Yeah.
Bus.
That.
Yeah, I was looking for the streamline equation.
Okay. Yeah. Boundary layer effects causing bulk transport tends to appear in how the rivers meander off. It also is sometimes used in atmospheric circulation. Large particle aggregation. The fourth one is something which I added is because this is a major issue in how centrifuges are required to work. Basically, when we put certain solvents in the blood to separate out vitamins and other things for measuring, we need to take care about certain such conditions taking place. Yeah. And one of the final things is the layered latte. Oh, it's not the latte, but two more.
Yeah,
Wait.
very different.
Yeah. If we pour hot espresso over cold water or into milk, please put it to milk. Yeah,
Go.
faulty water so that we can have a
Yeah.
density difference.
Yeah.
So initially when you do it, you get this nice gradient. both changing because the coffee particles are moving where they want to move, and temperature is changing because the thing is getting cold. So yeah, we are diffusion of temperature is experimentally known to be approximately centimeters square per second. Fault, and again we are treating coffee like a fault. So pretty hard on we are treating coffee particles like fault diffusion. Coffee diffusion is not as well studied as fault is. It's easier to get constant for fault. So yeah, temperature equilibrium will happen within an hour. If I put a hot thing over a very cold thing, within an hour we are assuming all sorts of equilibriums will be reached.
What do you mean salt?
Salt is, let us say,
Coffee is different salt.
basically let us have a saltier medium, like a less salty medium.
So that.
Yeah, diffusion of salt between mediums.
So, but the other two particles are the same. The layers.
No, the minute layer, basically because of the temperature, the layers will start shifting. Because this part is the same.
In this case, the coffee particles and the salt particles are chemically different.
Yeah.
If you're considering salt it is not.
We are just taking the constant from salt. We are borrowing a value. So, initial state is we have a vertical density gradient and we have a horizontal temperature gradient. Now, the mismatch between fast thermal and slow conformational diffusion drives the convection gradient in this regard. As it is doing is, particle at the edge cools down, density increases in that for that particle. Hotter things are less dense. So it will come to below. Cannot go past the density interface. Cannot just get mixed. The density are different enough. Gets pushed horizontally at this point. Now it is what do you call? If back at the center warms up, rises or density decreases, repeats, creating these kind of convection currents. And as the fault diffusion starts occurring, these convection currents start getting contained within itself, leading to this kind of a stratification. Yeah. Within layer, mixing homogenizes color. Between layers, there is a sharp discontinuity. Thermal time.
What leads to the creation of these density interfaces?
What?
What leads to the creation of these density interfaces?
You just clear it out.
Why are these density interfaces within like the two copper form?
How much time will it take?
Why did it?
Oh, that is due to temperature, right? Some particles went downwards, and basically, originally anyhow started with two layers to begin with. Sure. Then this particle came, some particles, like the edge particles cooled down.
Yes.
Then reached the density interface. Sure. Now, there is a push horizontally of further tension. And now, again, this part is still, some parts of this is heated, right? They'll get heated up again a little and then rise upwards. But by the time they have done that, other parts have cooled down. And this is causing these both things to get a density difference. And that is causing this to happen. Basically, the big issue is that within the time this is happening, the temperature is happening pretty quickly. But within the time it is happening, the fault differences have started coming up. And those things are also causing this to occur faster. Basically, we know that this will not happen with, say, honey and water. If I get a big chunk of honey and put a bit of water on top, I will not get this kind of a thing happening. So we do know that some sort of a fault is required. Only a density interface will not do this. Now, why it is required is not very mathematically enough.
I think if we modeling this using solid, any conclusions we get out of this should be true for any arbitrary mixture.
Yeah, for any arbitrary mixture where the particle sizes are different. Problem is, it's not doing with pure mixtures. With honey, a pure enough mixture issue. If let's say we mix the water with some sort of a salt, I think we do get this kind of stratification patterns. So again, problem is we do not know much of the details in that regard. Yeah. And this is their ability. Problem is again, the best experimental prediction they're able to get is 5 mm, and the actual number is 6 or 7 mm. This is a pretty such things in nature as well, where two things are diffusing against each other. This is one of the major reasons why certain oceans don't mix due to differing geothermal things. Iceberg melting also causes such things to happen. There's a reason that even if you heat up water very close to an iceberg, like volcanoes do erupt in iceberg areas. That does not cause icebergs to melt. But if you start heating the iceberg towards the top, it does start melting very quickly. And Ryan could tell me more on this. Star formation has something to do with it. Sorry? Yeah. Ring particle. Coffee droplets evaporate on surface, and when we just put a normal coffee drop, when it evaporates out, we see a dark ring. This does not happen with other mixtures, by the way. I can get a coffee and I can get a black pepper and water mixture, and even on evaporation, I'll see a pretty homogenized mixture. So we are very interested in finding out why is this happening. Why doesn't coffee dry uniformly? Coffee is a suspension, not a solution. Oh, stupid error. This should be nanometer. Individual molecules are 1 nanometer. Individual molecules. Coffee grains are 10 to 100 nanometer in diameter.
One coffee bean covering the entirety of New York City.
New York City is.
Oh, but no,
It's
I'm
big.
coffee bean, not coffee. This is coffee.
That's why I said bean.
So we have seen that on the other hand, water droplets with pepper, we don't see any ring form. Water droplets are much larger than pepper. In this case, it's just a factor of 10. In that case, it's a much larger than pepper. So yeah, naive expectation, droplet shrinks uniformly, leaving uniform stain. Reality, contact line is pinned by the surface with roughness. Droplet radius is fixed, contact angle is fixed, height decreases by radius stay constant. Okay, please note the time lapse. In this case, we can see the radius is not shrinking at any point. The height of the coffee of the droplet decreases. And secondly, if you look at this, here evaporation is not happening for all ends. Like this angle remains constant in coffee's case. If you take a look from the side. So yeah. So if contact line is pinned and evaporation is uniform, liquid must flow inward to supply lost volume. However, evaporation is not uniform. Particles, colloids carried by flow concentrate at the edges. Water vapor concentration in air above the droplet. Steady state diffusion equation is. So boundary condition is we'll have everything will become equilibrium at infinity. At the droplet's edge, no evaporation is happening because the right at the edge there is no water really to evaporate. And the substrate is not evaporating. We cannot assume that coffee is not evaporating away. So we will just make the droplet complete via mirroring it downwards. Problem equivalent to symmetrified droplet without substrate loss. Due to sharp tip contact angle, gradient of evaporation is diverging, and two words I do not know the answer to, not know the meaning to, even though I have one of them as my course.
Here?
Basically, there will be much more evaporation towards the edges. They'll evaporate much faster, moving almost all the liquid towards the center and leaving all the substratum there. Yeah. So larger reverse flow is needed. The radial velocity is especially large on the contact line. Carries particles efficiently to the boundary, creates a sharp dark ring. Now, something which are known as that in this case, we want the surface to be rough. It is much easier to see this on the rough side of a paper than on the smoother side of the paper. We want the surface tension to be like the water should not be messed much to like let's hope this experimentation fail. Particle size coffee grind does matter in this case. And yeah, larger particles like pepper cannot be carried as efficiently in this regard. Different surfaces of substrates rings are suppressed entirely. So again, still it works. Anyway, 1 cup we could get 6 phenomena out of it. Why coffee cups? This is why the paper reviews that coffee cup is a great idea, because they are universal, they are low cost and have no safety issues. We can do 6 phenomena with them and connect scale to everyday experiences, and it was a great icebreaker at the conference where it was given.
Keep spelling
And
that.
that complete.
Bringing them at the transform mode.
I think saying coffee cups present no safety issues is a bit presumptuous.
Yeah. Considering we were assuming almost infinite temperature is fertile liquid. It raises questions on how safe is infinite degree water. Maybe it is safer than whatever these people are doing in the environment. Yeah, I'm closing the recording.